So now let's talk about the law that started it all. Boyles-Charles, Gay-Lussac's combined gas law, all of them developed from the ideal gas law. The ideal gas law came first, and it all centers around the idea that gases behave perfectly under all situations, because that is what is defined, that's what defines an ideal gas. Now, actually, and this is going to sound really strange, but if you look up an ideal gas in the back of your book, it actually says an ideal gas is one that behaves according to the ideal gas law. And Rule 1 in English class when I was growing up was you never define a word with the word. So I changed it a little bit to say it behaves perfectly. Now, what do I mean? What I mean is, if you're talking about Boyle's law, then the ideal gas, when you double the pressure, the volume will go down by a half, exactly a half. No slight variations, no anything. Now, obviously, we don't live in an ideal world. We live in a real world, and there are such things as real gases as well. And we're going to talk to them at the very end of this whole unit. So, but for the most part, if we don't talk about things in an ideal situation, it makes the calculations really difficult. So let's assume that all gases behave perfectly under all situations. They're going to behave according to the ideal gas law, which is PV equals nRT, or sometimes you'll hear me call it as PIVNR. So in PV equals nRT, the pressure is in ATMs, and that's P. V is your volume, and that's going to be in liters. T is your temperature, and that is going to be in kelvins. R, now this is very important. R is what is called the gas constant, and the gas constant for our class is going to be 0.0821. Now, there are several gas constant values, and each of them have a different value based on these two units in particular, atmospheres and liters. You can have one that has kilopascals, you can have one that has millimeters of meters cubed for volume. So, and the value is going to change accordingly. We really would prefer to keep it in atmospheres and liters. They're the easiest two units to convert to. So here's the thing. Do you need to memorize this number? No, you don't need to memorize it. I will always give it to you. But you will use it so often that it'll become second nature to you, because you're always going to be putting things in atmospheres and liters. And then N is the only factor we really, the only other factor we don't know. And N we actually do know, we've just never seen the symbol. N stands for moles. And of course, we're going to come back to mole conversions again. Now, one other thing that you may see as you're doing ideal gas problems is you may see the phrase STP. STP is not a motor oil. It is not Stone Temple Pilots. It is standard temperature and pressure. Okay, so you're talking about a temperature of 0 degrees Celsius and a pressure of exactly 1 atmosphere. So sometimes they'll say a gas is being held under standard conditions. Whenever you see the word standard, always assume that it means 0 degrees Celsius and 1 atmosphere of pressure. So let's use this law in an actual example problem. A 1.25 gram sample of CO2 is contained in a 750 milliliter flask at 22.5 degrees Celsius. What is the pressure of the gas? Now, here's the thing about ideal gas law problems. They look very different from every other problem. And the reason for it is, notice that in all the other problems we've done so far, we've always had two sets of conditions, a P1 and a P2, a V1 and a V2. But in ideal gas law, we only have one set of conditions, meaning nothing changes. This is where it is at now, not where is it going to be in 10 minutes. Okay? Now, because we're doing a calculation problem, the first thing you should always do is write down your formula. Fill in what you know, or write down what you know. My P is what I'm looking for, because it says, what is the pressure? The volume is 750 milliliters. Now, I just told you that we don't want to work in milliliters, we want to work in liters. So the first thing we're going to do is divide by 1,000 and get 0.75 liters. My moles. Now, do I have moles? No, I don't have moles anywhere in the problem. It doesn't say this many moles of carbon dioxide, but it does tell me that I've got 1.25 grams. So I'm going to do a quick mole conversion. I'm working with CO2. 1 mole goes on the top because I'm converting 2 moles, and the weight from the periodic table for carbon dioxide is on the bottom, which is 44.6 0.01 grams. Pull out my handy dandy calculator. 1.25 divided by 44.01, and I get 0.0284. Now, sig figs are not important here because it's not my final answer. So I'm going to write 3 sig figs, but I don't actually have to keep 3 sig figs when it's all done. I'll reevaluate the sig figs at the very end. And then lastly is my temperature. And my temperature is 22.5 degrees Celsius, but of course we have to convert to Kelvin by adding 273. So I get 295.5 kelvins. Plug everything into the formula. P is what I'm solving for. My V is 0.7500. My N is 0.0284. My R is 0.0821 because that's always going to be the same value. And my T is 295.5. Now here's the thing about these problems that people get stuck on, and this is a great way to mess up. You have to kind of plan out how you're doing the problem in your head before you actually go and solve it. Ideally, you want to be able to do the temperature calculation in your head. You don't want to have to pull out a calculator to do that. But even if you do, it's okay. But try to make the mole conversion the last calculation you put into the calculator, because you want that number to be on the calculator screen when you go to do the next step, so that you don't have to rewrite or retype anything. Remember, every time you touch the calculator, you increase the chance for making a mistake. So you want to reduce down those mistakes as much as possible. So I hit times. It's got my moles already in there. 0.0821 times 295.5. Enter. Divide by the volume, 0.75, and I get 0.91875, blah, 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 blah. Atmospheres. But obviously, that's not my final answer because I have to put in the correct number of sig figs. So I go back to my original givens. I have 3 sig figs in the mass. I have 4 sig figs in the volume, and of course I don't look at the degrees Celsius for sig figs. I look at the kelvins, which are 295.5, which is 4 sig figs. So my fewest number of sig figs is the mass, which is 3. So this becomes 0.919 atmospheres. Okay, not so bad, right? Let's try another. What volume will 50 grams of ammonia gas, NH3, occupy at a temperature of 0 degrees Celsius and a pressure of 1 atmosphere? And of course, we know when we see these two things, they are talking about STP. Okay. Does that affect the problem? No. You do this problem the same way. I'm just throwing it out there so you remember it for later. Okay. Write down your formula. PV equals nRT. My pressure is 1 atmosphere because it's at STP. My volume is what I'm looking for because it says what volume. My N, again, I don't have N, but I do have grams. And of course I can do a mole conversion. So let's quick do the mole conversion. 1 mole on the top. 17.04 is the weight of ammonia. Whip out the calculator and I say, okay, 50 divided by 17.04 is 2.93. Then T is going to be 0 degrees Celsius plus 273, which is obviously 273. Okay, plug everything to the calculator. I'm sorry, plug everything into your formula. 1 is the pressure, V is my volume, what I'm looking for, 2.93 is my moles, 0.0821 is my R, and 295 that's the wrong problem. 273 is my temperature. Go back to the calculator. My moles are already up there. Times 0.0821 times 273 is 65.76 liters. Go back, evaluate my sig figs. 3 sig figs, 3 sig figs, 2 sig figs. Oh, I got around it. 66 liters is my final answer. And that's how you do ideal gas law problems.